It is my great pleasure to welcome you to the world of learning new concepts and current trends, so let's start. As software grows to hundreds of thousands of lines, the primary challenge becomes managing the data paths. Without a clear structural strategy, developers often resort to redundant code blocks that become increasingly difficult to coordinate. Duplicating state logic across an application increases the memory footprint. When a change is required, every instance of that duplicated code must be manually updated, creating a high risk of synchronization errors. Object-oriented programming solves this by organizing code into distinct, reusable models. Instead of writing logic from scratch, developers build modular templates that manage their own state. Look at the difference in data flow here. On the left, a flat system relies on isolated, duplicated data blocks. On the right, a hierarchical system groups related logic into a tree structure, where lower nodes draw directly from a single parent node. Because they are connected, modifying the parent automatically pushes updates down to every dependent block. Java manages this hierarchical architecture through two specific mechanisms. Inheritance defines the rigid, structural relationships between objects, while polymorphism dictates their dynamic behavior at runtime. Inheritance relies on a strict is-a relationship. It allows a new, specialized class to seamlessly absorb the properties and methods of an existing parent class. Mastering Java requires moving past basic syntax to understand how these hierarchical structures share state, enforce strict initialization routines, and decouple an object's reference from how it actually executes at runtime. The foundation of this system is the superclass. This acts as a generalized architectural blueprint, establishing baseline variables and methods that other classes can use. Here we have a class called bankaccount. It defines a baseline state with a private balance variable and a public method to deposit funds. To create a specialized version, Java uses the extends keyword. By writing class savings account extends bank account, we create a subclass. This implicitly absorbs the deposit method and balance data structure from the previous class. They exist inside the subclass, though not explicitly typed again. This connection satisfies the semantic is-a mapping rule. As far as the system's logic is concerned, a savings account is a bank account, just with additional features. This sharing of data introduces a conflict with encapsulation, the principle of protecting an object's internal state. Java enforces a strict access constraint. While private variables from the superclass are structurally inherited by the subclass, the compiler blocks the subclass from accessing them directly. This demonstrates what happens when that constraint is violated. Subclass BB attempts to modify integer j, marked private in parent class AA. The compiler throws an access violation error. Private scope is absolute, immune to subclass overrides, ensuring the parent's data remains locked down. To interact with that inherited private state, subclasses must route their data through the parent's public getter and setter methods. This routing guarantees that specialized downstream code cannot bypass validation checks or accidentally corrupt the core logic defined in the parent blueprint. Inheritance provides massive structural expansion, but it forces subclasses to strictly respect the memory and access boundaries established by their parent blueprints. Once the static class architecture is defined, we have to look at how these objects are actually instantiated in the Java Virtual Machine's memory heap. Creating a child object triggers a specific order of operations sequence. Because the object contains inherited traits, multiple layers of code must be initialized. The JVM enforces a rigid rule of instantiation. Constructors always execute in a top-down sequence, starting from the highest parent class in the hierarchy. This code sets up a three-level hierarchy: AAA at the top, BBB in the middle, and CCC at the bottom. Calling new CCCC on line 32 doesn't start by building CCC. It jumps to the top, executing AAA's constructor first, then resolves downward. A parent object must exist fully formed in memory before a child class can safely append its specialized state. Developers control this upward execution chain using the super keyword. When called as a method, super keyword must physically be the first statement executed inside a subclass constructor. If a developer omits this call, the Java compiler invisibly injects a default no-argument super call to enforce the top-down initialization rule. The super keyword has a secondary utility. It can resolve naming collisions when a subclass hides a parent's variable. Here, parent class persons declares a string called name on line 5. The subclass student declares an identical variable on line 19. Because the subclass shadows the parent, line 29 uses super.name to bypass local scope and retrieve the hidden parent state. Java enforces this predictable top-down memory initialization to ensure complex objects are built on stable, fully resolved data foundations. With structural stability established in memory, software also requires dynamic, adaptable execution paths at runtime. This adaptability is achieved through method overriding. This occurs when a subclass defines a method with the exact same name and type signature as a method in its superclass. Overriding completely replaces the parent's default behavior, substituting it with a highly specialized subclass implementation. This introduces a core concept in object-oriented programming, separating the reference type from the actual object type in memory. Here, on line 28, a generic variable named payment is declared using the superclass type payment. Moving to lines 30 and 33, this single reference is dynamically reassigned to hold completely different objects, first a credit card payment and then a PayPal payment. Even though the exact same payment.pay method is called both times, the executed logic changes depending on the specific object currently held in memory. This capability is called runtime polymorphism. A single interface instruction triggers specialized, multi-form execution paths. Rather than deciding which method to run when the code compiles, the JVM dynamically looks up the correct behavior based on the object's true identity at the exact moment of execution. If a third, entirely new payment subclass is added to the system, the generic instruction will route directly to it without requiring any rewrites to the overarching system code. Developers can write logic against generalized superclasses, eliminating the need to hard-code endless loops of type-checking conditions. Polymorphism removes brittle if-else ladders that try to manually dictate behavior based on an object's identity. This structure enables the standard Java design pattern of one generalized interface, multiple specialized methods. While inheritance acts as the static blueprint for complex applications, polymorphism is the active engine giving those structures power to dynamically adapt and scale.